Look, artificial intelligence isn't magic, right? It's machinery. Welcome to this explainer, where we're actually going to pop the hood on these intelligent systems and decode their exact anatomy. We're cutting through all that hype and buzzword bingo to understand exactly how these systems are structured to perceive, think, and act. By tearing down those conceptual barriers, we can see how some seriously complex algorithms are just assembled into logical, understandable pieces. Pieces that literally drive the tech we interact with every single day. Let's get into it. Here's our roadmap for today. First, we'll cover the foundations of AI. Second, we'll meet the intelligent agent. Third, we're mapping the agent environment. And finally, solving problems by searching. Building an AI fundamentally boils down to 4 sequential steps, kind of like a mission checklist. First up, formulating the exact problem and identifying its key components. Next, you gotta identify the agent, its specific capabilities, and the environment it's actually going to operate in. Then, deploy those agents to solve the problem. And ultimately, calculate and select the absolute optimal path to success. That, right there, that's the complete life cycle of how AI actually gets to work.
All right, Section 1, Foundations of Artificial Intelligence, the big picture.
To really understand AI, we have to recognize that studying it is essentially about mapping cognitive functions directly into computational models. At its core, we're looking at the categorization of intelligent systems. We need to figure out what makes a system merely automated versus truly intelligent. Think about a basic automated thermostat. It just reacts to a temperature threshold, right? That's just hard-coded automation. But a smart grid, one that anticipates power surges based on incoming weather patterns and human behavior, now that is artificial intelligence. An AI program is basically a carefully assembled set of components designed to mimic human-level reasoning. Getting a handle on the structural baseline lets us grasp the various sub-areas of AI operating all around us in real time, moving from simple reactive machines to systems that can actually learn and adapt on the fly. Tracing this tech from its early history right through to current trends shows us just how incredibly rapid the evolution of these intelligent systems has been. And we don't just look at the past decades of AI for trivia's sake, we do it to understand the trajectory. I mean, we've jumped from early symbolic AI and those rigid expert systems of the 1980s right into a present day that is entirely dominated by neural networks and machine learning, applications that touch literally everything from healthcare diagnostics to financial markets. And by studying this timeline, we can accurately project into the coming years. We can start anticipating trends like advanced edge computing and autonomous systems that are absolutely going to redefine how our digital and physical worlds intersect. Okay, Section 2. Meet the intelligent agent, the core actor. So if artificial intelligence is the broad underlying theory, the intelligent agent is where the rubber finally meets the road. An intelligent agent is essentially the physical or software embodiment of the whole AI concept. You can think of an agent as any entity that can perceive its environment and then take calculated actions within that space to achieve a specific goal. This continuous perceive, think, act loop, it's the actual heartbeat of any agent. Whether we're talking about a super sophisticated piece of software scraping data to recommend your next binge watch, or a physical robotic arm sorting packages on a warehouse floor, the defining characteristic is always the same. This active, continuous loop of reading the room, processing the data, and making a move. Now here's a crucial point. Rationality in AI has absolutely zero to do with human emotion, morality, or philosophy. It is purely about mathematical performance. A rational agent is simply one that takes the action most likely to maximize its chances of success based entirely on what it perceives and whatever built-in knowledge base it has. If an agent's goal is to win a game of chess, a rational move is simply the one that statistically increases its probability of checkmate given the current board state. It's all about making the optimal choice given the available data, totally removing any human bias or hesitation from the equation. If we look under the hood, the internal structure of an agent really just boils down to 2 highly codependent things: the architecture and the agent program. You can think of the architecture as the physical hardware, right? The camera lenses, the robotic servos, or the silicon processors. The agent program, on the other hand, is the software driving the decisions, like the computer vision algorithm processing the pixels captured by that camera. Just like a biological organism relies on both its physical body and its brain, you literally cannot have a fully functioning intelligent agent without both the hardware architecture and the software program working together in perfect, seamless sync. Standard agents are kinda rigid. They operate on strictly pre-programmed logic. They see X and they do Y. If a specific condition isn't met, they might just fail entirely. But an advanced learning agent, that is completely dynamic. It practically rewrites its own rulebook. A learning agent can actually operate in completely unknown, novel environments and get more competent over time. It constantly evaluates its own performance, soaks up feedback from its environment, and actively upgrades its internal logic to make better, faster, and more efficient decisions down the line. It's a real game changer. This is the difference between a machine that just follows orders and one that actually learns from its mistakes.
Moving on to Section 3, mapping the agent environment, the playing field.
Look, an agent is really only as good as its ability to navigate the space around it. The specific nature of a task environment completely dictates how complex our agent needs to be. It's a constant, looping interaction between the two. But environments vary wildly, right? We have to ask ourselves, is the environment fully observable, kind of like a chessboard where all the pieces are visible at all times? Or is it partially observable, like a self-driving car trying to navigate through heavy fog, where the complete picture is totally hidden? Is the environment static, meaning it doesn't change while the agent is thinking, or is it dynamic and constantly shifting? Accurately identifying these specific environmental traits is a massively critical first step before we even attempt to write a single line of code. So, how do we define all this? Well, every agent's environment can be mapped out using this awesome framework known as PAES. That stands for Performance, Environment, Actuators, and Sensors. Let's apply this to a concrete example, like designing an automated, self-driving taxi. First, you define the performance measure. Success looks like reaching the destination safely, legally, and, without spilling the passenger's coffee. Second, you map the environment, which includes the roads, surrounding traffic, pedestrians, and weather. Next, you determine the actuators. These are the physical tools it uses to interact with the world: the steering wheel, the accelerator, the brakes. And finally, you equip it with sensors to perceive its surroundings: cameras, LiDAR, radar, GPS, the whole shebang. Mastering this exact PAS representation is foundational to conceptualizing any functional AI. All right, let's wrap this up with Section 4, solving problems by searching, the mission. This is where things get really fun. An agent transitions from simply existing to actively making an impact by becoming a problem-solving agent. These are a specific type of goal-based agent, but before they take any physical or digital action, they go through this rigorous process of actually formulating the problem. They take a complex, messy, open-ended, real-world goal and mathematically translate it into a discrete, structured sequence of states and actions. They rigidly define the starting point, the absolute final goal, and meticulously map out a searchable state space of literally every possible step in between. And once a problem is formulated, the agent actually solves it by searching through this massive branching tree of possible solutions. It doesn't just guess, okay? It calculates. The agent looks at different paths and weighs the computational cost versus the efficiency of each route. Think about how the GPS on your phone maps out traffic delays, speed limits, and total distance to find your absolute fastest route to work. The AI weighs the cost of taking a highway with heavy traffic against taking longer back roads. It evaluates all that data, discards the slow paths, and selects the optimal solution based entirely on the specific requirements of the problem. That right there, that is problem solving by searching in action. The field of artificial intelligence is literally evolving by the minute. For sure, the absolute best way to solidify these foundational concepts, the agent structures, the environments, the problem-solving logic we've covered today, is to go out and reverse engineer the tools you use every single day. Seriously, open up your favorite app, whether it's a social media feed algorithm or a personal finance tracker, and try to isolate its internal agent structure. Look closely at the software you interact with, and see if you can identify its specific performance metrics, its actuators, and its sensors. It's like a giant puzzle once you know what to look for. So I'll leave you with this. If you had to build an artificial intelligence to tackle your own biggest daily challenge, how exactly would you define its PAES parameters? What is the specific performance metric of your personal daily grind? What sensors would it need to navigate it? By just thinking through that framework, you are actively applying the anatomy of AI. Thank you for joining me on this explainer. Keep questioning, and until next time, keep looking under the hood.